Hi everyone, thanks for checking out this video. So this is going to be a short video about how to simulate the Lotka-Volterra Predator-Prey model in R. And by the way, if you haven't seen it already, I've already made kind of like an introduction video to the Predator-Prey model without doing any coding, but just kind of explaining the model. So if you haven't watched that already, I'll link that in the description to kind of get like a general overview of the model. But for now, I'll just like quickly review the very basics of it, and then we'll get into the coding to write a simulation of it. Okay, so with the model, we have two variables, x and y. X represents the level of the prey population, and y represents the level of the predator population. And then, so basically, we have four terms here. So within the prey population, there's this like growth term here, which is a times the current level of the population. So that just shows that in the absence of everything else, like this population is growing exponentially based on how large it already is. And then we also have a death term for the prey population, and that's b times x times y, where b is a constant parameter, and again, x is the level of the prey population, and y is the level of the predator population. And so basically, one of the key points of this model is that the death term for the prey depends on the current level of the predator population. So that's why this term y is in this death term here, is because the predators are what's killing the prey. So that's why it depends on the current level of y. And then for our equation for y, we have a growth term, which is c times x times y. And this is the growth term for the predator population, and it depends on this this constant parameter c as well as y, and it also depends on x because for the predator population to be growing, they have to be getting enough of the prey to eat. So that's why it depends on the level of x here, and then we also have a death term for the predators, which is just h times y. And you guys might be wondering why I made the constant parameters a, b, c, and h rather than d. That's just because I thought that d would make it confusing, because we also have d in the ODs, like dx, dt. So yeah, these are both ODs, so they're just derivatives with respect to time, by the way. Okay, yeah, that's a super quick introduction. Again, if any of this is unfamiliar, please check out my other video that I'm going to link to in the description, going like more in depth on this model, like the basics. But yeah, for now, we'll just get into writing the code to do a simulation of this. Okay, so this code is going to be using Euler's method, which is basically like the simplest possible way to do a numerical simulation, like numerical ODE simulation. Yeah, nothing too fancy. It doesn't require any like external libraries or like any fancy software you have to import or anything. It's basically, yeah, like the least clever, simplest, like most obvious way to simulate a system of ODEs. So basically with Euler's method, if you're not familiar with it, basically what you do is you move through time in increments. So we'll be defining some like delta t sized increment, and we're going to like go through the simulation in these delta t sized steps. And at each step, we're going to calculate how the variables are being updated in that time period, basically. And we're just going to keep track of all the variables like that in these like delta t sized steps, and just kind of like inch our way through the simulation until we reach the endpoint of the simulation. So yeah, basically like the least clever, like most obvious way to numerically solve an ODE system. And it's nice because we can just write it from scratch in R. We don't need any kind of like fancy libraries or anything. Okay, so let's get into it. So I always start my R code with this command here. So this is just something that you can run to like clear the environment if you have to. In case there's any variables you have to just get rid of to start from like a clean slate. But yes, let's just clear the environment like that. And then, so what we're going to do, next is just define some starting values for x and y. So I'll call this x init and y init. So we're going to say x init equals 10. I'm not being too specific with the units here. You could think of this as being like 10,000 or 10,000 of like the prey population. Yeah, this isn't really supposed to be like an accurate ecology video. This is more of like a programming video, so I don't actually know if it's going to be like ecologically realistic or not. But yeah, I'll just say like we'll start with like 10 of like the prey population. This could be like hundreds or thousands in terms of the units. And then for y in it, I'm just going to start it at 1. Yes, I'll just run this for now to get these variables initialized. Okay, and then next we're going to define something called tn. So this is just going to be how long our simulation is going to run for. And I'm just going to say tn equals 50. Again, no specific time unit. This could be 50 weeks, 50 months, maybe even 50 years. Again, I'm not really an ecologist. This is more of like a programming tutorial, not like an accurate ecology video. So I don't know if this is actually realistic or not, but yeah, I'll just call it 50 for now. Could be months, years, weeks, whatever you want it to be. And then let's define some variables to keep track of our values for our constant parameters. So we have A, B, C, and H. So I'll say A equals 1.1, B equals 0.4, C equals 0.1, and H equals 0.4. Actually just got these from Wikipedia. You guys are going to see why when I run it. I picked these, like, I guess whoever wrote it into Wikipedia picked them specifically so that we could see something kind of interesting happen with the results. So you guys are going to see what I'm talking about in a second when we actually run the simulation. Okay. So now what we're going to do next is we're going to define some vectors to keep track of all of our variables as we're moving through time. So we're going to define a vector called x, which we're going to start it off with our x init. And basically what's going to happen is that as we move through time, we're going to be appending to this vector. So it's going to get filled up. Like it's going to be going like keeping track of the values like that. So every increment that we move through time, we're going to be appending the new value to this vector. But for now, we're just going to start it off with our value of x init. And then we're going to do the same thing for y. Just start off a vector, start it off with y init. And then lastly, we're going to have a vector keeping track of t, our time. And that's just going to start off at 0. And we're going to be appending to this in terms of our delta t sized increment. So it's going to be getting filled up like this, basically. Yeah, you guys are going to see it in a second. But yeah, this will start off at 0 for now. Okay, so you guys can see I've been like running these like one by one, but you can just kind of leave them all and then run them all at the end if you want to. But I'm just going to kind of run them little by little like that. Okay. And then lastly, before we start the simulation, we need to define our delta t. So I'm going to say delta t is 0.01. And again, this is the size of our time step. Remember, we're making time something discrete. We're going to be moving through time in like discrete steps. And each step we're going to be keeping track of how the variables are being updated, basically. So, whoops, made a little typo here, actually. It should be delta t. And yeah, this is going to be the size of our time step as we move through the simulation. Okay, so now what we're going to say is we're going to put all this like simulation in a while loop. We're going to say while, basically while the last element of our t vector, and we're going to write that like t index length of t. So that's basically just a way of writing the last element in our t vector. Right now it's going to be 0, but remember, this is going to be getting filled up. So yeah, it's going to be looking like that, and we're going to be like appending to it like that. So yeah, basically this command here is basically no matter how much we fill it up, this will always be taking like the last element of this t vector here. So we want to say while that is less than t end, then we're going to do this while loop. Okay, so this is going to be where the actual like the real simulation happens. So what we want to do at each time step is we want to have our like current values for everything. So I'm going to say current x equals x, kind of the same syntax here, just getting our most recent value of x, which is x, the vector at index length x. Oh, by the way, guys, just don't forget in R, the indexing starts at 1, not 0. So just make sure you keep that in mind. The first index is 1, which that might sound normal to you, but in programming that's actually kind of weird. Like most program languages start at index 0 and kind of go from there. But yeah, in R, the first index is actually index 1. So this is how we get the most recent value of x. And then yeah, we're gonna say the same thing. Same thing for y, basically. And then also, same thing for t. I'm kind of writing this like less efficiently than I have to, just to make sure it's clear for you guys. If I was writing it to be like optimal in terms of speed, I probably would not even write all of this, and I'd probably just like, yeah, I'll probably kind of skip over some of this and just write it differently. But yeah, I'm writing it this way so that it makes sense to you guys. Kind of just letting you guys know like what we have for our current values of the variables and our current time point at each time step. Okay, so now what we have to do is basically we have to calculate what our next what our like next value for the variable is based on the current value and then the delta of the variable. So if you guys haven't already watched it, I actually have like another video explaining Euler's method like on the whiteboard, kind of explaining really how it works in more depth. But I'm going to try to like kind of explain it now too, for like a little review. Yeah, so basically the way we're going to think of it is we're going to think of this like dt as being like really like a delta t. Sorry for this, you know, I know it looks kind of bad, but yeah, we're going to think, instead of like dx over dt, we're going to like discretize this and think instead in terms of like delta x over delta t. And then all we're going to do is bring the delta t over to the other side. So the way we can calculate the delta of x is just all of this times the delta t. And remember, we have our delta t here. So basically our delta x is going to be just this stuff evaluated with these constant parameter values and our current values of x and y times delta t. So again, I'm kind of doing this like sort of sloppily in this PDF here. But if any of this doesn't make sense to you guys, I'm going to also link to another video where I explain Euler's method like kind of more in depth. But yeah, hopefully this will make sense. Yeah, we're calculating the delta of these variables, and we do that by just taking these terms here and just multiplying them by delta t, and where we just plug in our current values for x and y and c and h. Just plug in, evaluate this term times delta t, and that's our value for delta y. And then our remember, like the delta y is like the change in our y for that time step. So the next value of y is just the current value plus the delta y value. So yeah, I hope that makes sense to you guys. If not, maybe it'll make more sense when I write it in code. But if it still doesn't make sense, then I'll also link you guys to my video explaining Euler's method on the board, and hopefully that'll make more sense. But okay, so yeah, I'm just going to say like delta x equals, okay, a little bit to do here, so it's going to be a times current x minus b times current x times current y. So basically all of this is just taken from this here, except instead of just having them being these like symbolic terms, all of these have some kind of numerical value. Like the a and b are defined up here, and then these are all some actual numbers at this point for current x and current y. These are all some actual numbers that we can like plug in. And then so it's all of that times delta t, which is also defined as a numerical value here. So basically, just to reiterate again, I know I keep repeating myself, but yeah, it's like delta x equals all of this stuff times delta t, which we just brought over to the other side to solve for delta x. So yeah, just all of this stuff times delta t, that's our delta x. And then our next value of x, I'll just call it next x, equals current x plus delta x. So basically just the deltas of the variables are the change in the variables for each time step. So the next value is going to be the current value plus the delta value. Yeah. So now we have now we've calculated our next value of x at the next time point based on our current time point value of x. And so now we just have to do the same thing for y basically. So I'm just going to say delta y equals okay, c times current x times current y minus h times current y. So again, that's just all of that here. And then remember, we're bringing the delta t over to the other side so that we can solve for delta y here. Remember, these things are just, instead of being continuous, we're just making them deltas so that we can think of them in like discrete terms. But yeah, so just all that multiplied by delta t. And then, yeah, same thing, just our next value of y is going to be the current value of y plus the delta y. And then, so same thing for t. So it's just, yeah, we already have our delta t up here. So we can just say, like, our next t equals current t plus delta t, and remember, we don't have to calculate delta t because we've already defined it up here. Okay, so now that we've calculated the next time point values for all these things, we just have to append them to these vectors to keep updating these vectors at each time point, basically. So I'm going to say x, remember this is a vector that we can append to, equals, append x next x. So this is basically just appending the next value of x onto this x vector. So it's just adding another thing onto the end, like it's going to be going like that. Okay, and then same thing for y and t. Okay, so y equals append y next y. And t equals append t next t. Okay, so that's basically everything we need to do. Yeah, all I'm going to do now, like, this is enough to run the simulation. All I'm going to do now is copy and paste in some code to plot the results. So first, I'm going to copy and paste in just plotting the levels of x and y over time. So, okay, so this plot here is just plotting, okay, sorry, I kind of made the letters a bit confusing because, yeah, for the plotting here, it's like we're actually plotting t on the x-axis and x on the y-axis. So sorry about making it a little bit confusing, but this is basically just like, forget about this confusing syntax for the plotting. This is really just plotting our level of x, which is the prey population over time, basically, and then down here plotting y, the level of the predator population over time. So yeah, first I'll just run this while loop, and then we can plot the results. Okay, looks like it ran okay, and then yeah, I'll plot the results. Okay, yeah, so this is kind of the interesting thing I was referring to. So if you set the parameters for the predator-prey model correctly, you can get these oscillations where they both kind of like go up and down in waves like that. And the biological like intuition behind that is that you basically have the prey population increasing, and then as the prey is increasing, the predator population is also increasing because remember, the growth of the predator population like depends on the level of the prey. So as you get more and more prey, you also get more and more predators. But then as you're getting more and more predators, they're starting to eat all of the prey. So then you're getting more and more prey dying off because of the increase in the predator population. But then as the prey dies off, then the predators aren't getting enough to eat, so they start dying off more. And then as the predators die off, then eventually the prey population recovers and goes back up, and then the predator population goes back up, and they kind of keep oscillating up and down like that for the right parameter set. Okay, so yeah, looks like it worked correctly. There's one more plot I'm going to show you guys. So this last plot I'm going to do is what's called a phase space plot. So basically this is like, instead of plotting the levels of the predator and prey as functions of time, we can plot the level of the predator basically as a function of the level of the prey. And this is what's called a phase space plot. So I'll show you guys how to plot this basically. Yeah, so this is plotting the level of the predator, y, as a function of the level of the prey, x. So yeah, again, this is just called like a phase space plot. Something could be interesting to look at in your analysis. You guys can like maybe play around, see how this changes with like different parameters and stuff. But yeah. So I hope this made sense to you guys. Again, if anyone is having trouble with like the basics of the predator-prey model or the like Euler's method, I'll also link to my videos going more in depth on like those two topics. I kind of give like brief reviews of them here, but yeah, if you're confused about any of that, I'll link to those two videos that'll hopefully explain it better. But yeah, other than that, if you guys have any questions, just let me know in the comments. I'll try to answer them. Also, the code will be up on my GitHub, like usual, if you guys want to download and try it yourself. But yeah, thanks for watching, guys, and see you next time.